So can all of you see the OneNote file? Can all of you
Yes,
see the
sir.
OneNote file? So okay. So expectation of a discrete random variable is we are studying. So this is x is a random variable which assumes these values and with density function. So can you tell me what is the density function? How do you define density function? Can anyone tell me? So you guys are not attentive. So what is a density function? So what is the by definition f of xi? So this is the probability of x is equal to xi. So this is density function. Then we define ex to be summation xi f of xi, provided mod of summation I is equal to 1 to infinity mod of xi f of xi is finite. Okay, if this infinite sum is finite, in that case we say this is x has, we say x has finite expectation and the expectation is defined before. And this is the expectation. Okay, this we defined in the last class. Now suppose something is given and we did some problem also, right? We did some example also with the expectation of on the expectation of a discrete random variable. Now suppose something is given like x1 plus x2. Suppose we know that the expectation of both these we know. So how to find the expectation of x1 plus x2 from the known expectations of x1 and x2? So this might not be. So we can do the other way. We can just simply calculate by the definition. Using the definition, we can simply calculate the expectation of x1 plus x2, or we can use some formula, some theorem, known results to compute the expectations of x1 and x2. So when we use this known results, so things become easier for us to do the computations. So for that we have these results, which was theorem 2. I again state the result. So let x and y be two random variables. With finite expectations, then so these are some known results which we mainly use to compute these combinations of random variables. This is then 1. If c is a constant, and p x is equal to c equal to 1, then p of x is equal to c. 2. If c is a constant, again if c is a constant, then cx has finite expectation and E of Cx is equal to C of Ex. This we can expect. So this is somehow something like this is linear. So this expectation is a linear function, a linear operator. and x plus y has finite expectation. And e x plus y is ex plus ey. 4 is p greater equal to x greater equal to y is 1 implies ex greater equal to ey. So you see everything is x greater equal to y. If that is 1, so that actually says all about the ex. So we need to know what in the sample space. Only we think about those sample spaces, those outcomes where the probability is 1. Okay. Then ex is equal to uy. Moreover, so the similar stuff you will see in something called not all of you. Okay, probably in my section, all of you are not. No one is from probably my section from mathematics. So in mathematics, if you learn we'll study something like something is called measure theory. When you study the measure theory, these things will become almost obvious. Okay. Up to this part, things are almost same as measure theory. Some particular case of measure theory up to this part, and X has finite expectation if and only if mod X has finite expectation. So these results we saw in the last class, and if mod of Ex is less equal to E mod X. So these results we saw in the last class, and we prove this, and these three now we'll prove. After that, we will prove 4. Okay, so now to prove 3, we need something more, which is called discrete random vector. So which also I defined in the last class. To prove 3, we need this thing, and from 3 we will prove 4. So we will define now, we'll introduce discrete random vector. So this is something very much like a discrete random variable. So discrete random variable we define a map X from the sample space to R such that P X is equal to some Xi, and this assumes some finite or countably infinite values such that this is Zen event. Similar case happens here. So this is a map X from omega to r power r. Instead of r, we are taking r power r, which assumes some finite or infinite, countably infinite vectors in r power r, and the probability x is equal to xi is an event. Okay. Now, if suppose x1 and x2 are two random variables, so discrete random variables, then we define x omega, where omega belongs to the sample space, as x1 omega comma x2 omega. This is also a discrete random variable, discrete random vector. This is a discrete random vector, and we define the joint density function f of x1 comma x2 is by definition P x1 is equal to x1 and x2 is equal to x2, which is called the joint density function of this is basically the density function of the discrete random vector capital X, and this is called the joint density function of x1 and x2. And we define for phi a real valued function on R power R. We define this way: summation phi x bar f of x bar is nothing but, by definition, we're taking the, this is our notation, actually our notation. So we are taking the summation over all the values of this discrete random vector x. So this is so this we define. Up to this we did in the last class. So where x is a random vector, discrete random vector. So from here we will start today's class. Okay, I actually spent a lot of time for the recap. Yeah, okay, any questions do you have? So this is the theorem, this theorem 1 late. So we use the theorem 1 to prove theorem 2, 3, the third part of theorem 2. So let X be a discrete random vector having density F if and let phi be a real valued function on R power R then the random variable z is equal to phi x we are getting a new random variable, discrete random variable, z is equal to phi x, has finite expectation if and only if mod of phi x bar. So this definition, what is this thing we defined here before we have defined this? This is equal to finite. In this case, we say that phi of x has finite expectation, and then E of z is equal to summation phi x bar f of x bar. Okay, any questions till now? We will use this theorem 1 to prove theorem 2, the third part of theorem 2. Any questions so far?
Sir, expectation is defined as sigma x f of x or sigma mod x f of x.
Expectation is defined as sigma x fx. You see, we define the expectation. I go back there. Expectation is this: summation sigma xi fxi varies from 1 to infinity. But we say this is finite, this expectation is finite if this summation mod xi f of xi is finite. Is this okay? Any questions here? Any
So
other
less
questions?
than infinity is written to verify if it is finite.
Yeah, less than infinity is written to verify this. So this is finite, implies this is finite. Okay, but this is the expectation.
Okay, sir.
And this is true means we could just say that this is also finite. Okay, but this expectation should be independent of how we arrange this xi. So what is xi? Suppose what is x100? You can also put as x. You can put some other random variable and make this x100 to be x1, x200 to be x2. This way you can rearrange the terms. Okay. And if you rearrange the terms, the summation, the expectation ex should be the same. So that is that holds if the summation mod xi, here this mod x count, if mod xi f of xi is finite, in this case if you rearrange anyway, this ex will be always finite. So that's why this we call this absolute convergence. This absolute convergence is needed. Any other questions? Good, very good question. Ask this type of question. Okay, now we go to proof 3 of theorem 2. So first proof 3, what is 3? 3 is that if x and y are, this is the 3, if x and y have to be two random variables, discrete random variables, this discrete random variables, everything is discrete here, with finite expectations, then x plus y has finite expectation and e of ex plus y is equal to ex plus ey. We will first prove this, then we will prove 4. Okay. So here we just use the previous theorem, theorem 1. So you can understand very easily that here phi of, so what is phi? Phi is a map from r power r to r. Here is a phi is a map from r power 2 to r. So here phi x plus y is x comma y is x plus y. And we have to show the summation x bar. So x bar mod of phi x bar f of x bar is finite. Now this is just 1 second. Professor Ganesh sir, I am in class. So after the class ends, I will call you. Is that okay? So here summation x bar phi of x bar f of x bar, this is by definition I, so 1 to infinity mod of phi xi bar f of xi. Okay, so xi bar. So this we write as phi x comma y, xi comma yi, f of xi comma yi. Now this is nothing but by definition of phi, this is xi plus yi f of xi comma yi. Now this is less equal to I is equal to 1 to infinity mod of xi f of xi comma yi. Just 1 second. This is okay. I should not write this word. Okay, so there are two variables. Okay, so that's why I'm not writing this in this ij. I'm just writing in x and in terms of x and y. So you can just write in ij. Then you have to actually handle two variables at the same time. Then you will get the same results. You can also using the variables I and j. You can do this. There is no problem. But you have to handle the two variables I and j. So that's why I am writing in an easier way. So this is nothing but x comma y phi x comma y f of x comma y. So this is summation x comma y mod x plus y f of x comma y, which is less equal to summation x comma y. This will break mod x f of x comma y plus x comma y. So this part is actually important, so which I was missing in the last attempt. So all of these things you may not understand now because there is something called multivariate distribution which have not been taught yet. So that's why this is a little bit difficult might be, but these are not difficult. For now it might be as difficult to you, but these are not that difficult. So here this will be, but still if you have any question please ask me. Mod x, we are fixing this x and you are putting this y here as y, we are fixing this y and putting this summation x here. So in this case the x is fixed and in this case the y is fixed, and if we take this summation we'll get, so this summation will be the density function of x, and this summation similarly will be the density function of y. So this is finite. So we see that this thing is finite. So x plus y has finite expectation. What is happening here? So see, there are two random variables here, x and y. So in this case also, but we are putting this x out. So in this case, x is fixed and y is varying. Now this is the joint density function of x and y. If we fix y, if we fix x and take the summation, what we'll get, that will be the density function of the random variable x. Is this clear? So this you will see again when you go to the multivariate distribution, you will see all this thing. But this is almost clear, right? So x and y are two random variables are going. If you fix, when you are taking all the, you fix x and you are taking all this y, when the first component is x which is fixed. Now if you take all this fxy, if you take the sum, you will get if the density function of fxy, fxx, the density function of x. The joint density function, if you fix one component, one coordinate, and take the summation, what you will get? You will get this density function. Is this clear to you, or do you have any questions? Then you can ask. Plus y. Okay, and if you don't understand this, don't. It's okay because we'll discuss this in details when we'll discuss. multivariate distribution. So this is again phi of x plus x comma y, f of x comma y, which is x comma y, x plus y, f of x comma y, and this is again, we'll break this summation, x comma y, x, f of x comma y plus x comma y, y, f of x comma y. Now fix x and vary y. Again here fix y and vary x. So this will be, you will get, if you fix x and vary y, this joint distribution function, you will get the joint density function, you will get the density function of x. Similarly here, if you fix y, here y is fixed, and if you vary x, then you will get the, and take the joint density functions, if you take the sum, you will get the density function of y, and that is equal to ex plus ey. Okay, so ex plus y is equal to x plus e. Any questions? Any questions any of you have? Was this difficult to understand why we can make this joint density function? We can take the joint density function, fix one variable, take the sum varying over y, and that will be the density function of x. Is that okay to all of you?
Sir.
Yes, sir.
Sir, what is the significance of this equation?
Which equation?
The theorem that we have proved.
Okay, this you will see when you will do the problems. In problems, so suppose if a variable, if a random variable, discrete random variable, you can write as x plus y, and it might be easier to compute the expectation of x and y. In this case, the new variable z, which is x plus y, which is just the expectation is just ex plus ey. You don't have to compute by definition, using definition, you don't have to compute the expectation of z equal to x plus y. You
Sir,
know
any example?
Yeah, we'll do these examples later, not now. Okay, okay, just wait for maybe half an hour. I'll come to all these examples. Okay, there is one example, but just wait for half an hour. Any other questions? Okay, now we go to the fourth part of theorem 2. Fourth part is this. So px greater equal to y equal to 1 implies ex is greater equal to ey. And moreover, if this happens, that is px greater equal to y equal to 1, in this case ex is equal to ey if and only if px plus y equal to 1. So we will prove this now. So let z is equal to, see, even to prove this part, we need the previous part 3. Let z is equal to x minus y, which is x plus minus y. Okay, so Ez is equal to e x plus e minus y, and e minus y is equal to minus of ey. So this is true by theorem 2. Here, if c is a constant, then cx is a finite expectation. Here c is equal to minus 1. and E of Cx, E of minus x is equal to minus of Ex. Okay. Now let Zi prime be a value of Z such that Zi prime, so is a value means Z is a random variable, discrete random variable, so Zi is prime is less than 0. So P of Z is equal to Zi prime is 0 as P x greater equal to y is equal to 1 implies P z greater equal to 0 is equal to 1. So something is negative, that probability is 0. Okay, is this fine? Any question here? Is this okay to all of you? Okay, so we'll compute Ez. See, Ez will be summation z fz. Now, if z is negative, in this case, fz, what is fz? Is nothing but z is equal to small z. So, if z is negative, in this case, fz is 0. So, this is always greater equal to 0. So, this implies ex minus ey is equal to Ez is greater equal to 0. So, this implies Ex greater equal to Ey. Okay. Now, suppose, so here we assume that P of x greater equal to y is equal to 1. This implies Ex greater equal to Ey. Again, if we assume P, okay, if we assume P x is equal to y, this is 1, that implies P x less equal to y, which is even bigger than P x is equal to y. So, and this is equal to 1. This implies P x less equal to y is also probability 1. Okay. So, P x less equal to y, it has probability 1. This implies P x is less equal to Ey. So these two implies this and this. These two implies Ex equal to Ey. Okay. Now we'll do the converse part. So suppose Px greater equal to y has probability 1 and Ex equal to Ey, that this implies Ez equal to 0. Now, just we did in the last case, here also, again here, if Zi prime negative be a value of Z, then P of Z is equal to Zi prime is equal to 0. So that implies f of Zi prime is equal to 0 is equal to 0. So this implies that Ez is equal to summation z fz. So this is a sum of non-negative terms. So, and this is a sum of non-negative terms whose sum is 0. That implies if zi greater than 0, to be f of zi equal to 0. So p of z is equal to 0, so is equal to 1. So this implies p of x is equal to y is the probability of x is equal to y is 1. So these things are not difficult at all. But yeah, so I have proved all these things. If you have any difficulty to understand this, please let me know at which part you have difficulty. These things are not difficult at all, and you have to do this on your own. Then you can play with the probability of events. Okay, is there any difficulty to understand any part of this? Please tell me. Fine. Okay, there are some more theorems which I am just stating. I am not proving because I don't have that much time to prove, and this course is not much theoretical proof, much theoretical course. So this is about if we can give some bound to the random variable, then we can also give some bound to the expectation. This is that theorem. So let x be a random variable and for a constant a m, p of mod x less equal to, so this is the bound I am giving. I am saying that p of mod x less equal to m, this is equal to 1, then x has finite expectation and mod of ex is less equal to m. Okay, so this is very important, that at the points at which p of means the point at which the mod x is less than equal to m, this is bounded by m, that has probability 1. Or in other way, if something has value greater than m, that has probability 0. That has probability 0. So this is something. There is what we talk about. We have seen that if x and y have expectation, that e of x plus y is equal to x plus ey. So the expectation is additive. It has this additive rule, that is e x plus y is equal to x plus ey. But can we expect that this is also multiplicative? That is ex into y. That expectation is equal to ex into y, ey. Can we expect this? Is e of x into y is equal to ex into ey. So answer is, in general, this is not true, but we can give so in general this is not true. So we can give many examples, and very easy examples we can give to show that in general this is not true. But if we put some conditions on x and y, then we can expect some result, and the result is let x and y be two independent random variables having finite expectations as usual, like the other. So we are doing everything for these random variables which have finite expectations. So this is discrete. Everything we are doing so far is about expectation, is on the discrete random variables. So these are independent, which is very important. And okay, not and, then x, y has finite expectation and ex y is equal to ex into ey. So x and y are independent random variables. What does it mean? So this is not yet taught, but you have seen independent events, right? You have seen when two events are independent, that you have seen. We can similarly define when, so these things will be again taught in details, but here we need these things. So x and y are independent random variables when, so this is for discrete case, p of x is equal to okay, some, how will say, x belongs to A, intersection y belongs to B for any two events is equal to P x belongs to A into P y belongs to P. Okay, so in particular, P of x is equal to x, y is equal to y. This will be P x is equal to x into P y is equal to y. So that means the joint density function fxy is equal to the product of these two individual density functions. So this is the property of independent random variables. So f x comma y is equal to fx into fy. Okay. So we have to just use this thing. So here summation x y x comma y f of x comma y is summation x comma y mod xy, and we break this fxy as fx x into fy y, and this is equal to, we can break this in these two things, mod x fx. So this we can break because all the terms are finite. This is because all these two separate terms are finite. That's why you can break this way. So this is finite. So xy has finite expectation, and similarly you can prove that E of x y. So I am not proving this. So almost similar proof. EXY is equal to EX into EY. Okay, any questions? Okay, there is another theorem which might be important. So I am also stating that theorem. So these things actually we need to prove the expectations of many things, many random variables. Let x be a non-negative integer valued random variable So I defined what is integer valued random variable. So the assumes the values it will assume those are non-negative integers. So everything discrete. So here this is discrete. Okay, so non-negative integers value means this has to be discrete. Then x has finite expectations. If and only if summation x is equal to 1 to infinity, because these are non-negative integers valued. So others we don't need to consider. This is finite. Okay, so this means this converges. And if the series converges, this converges, then Ex is equal to summation x is equal to 1 to infinity P of x is equal to x greater equal to x. Okay, so these also are not, this is not very difficult to prove. We have to just change some summation sign, only that thing, and some change of summations, then you can prove this thing. So I'm not proving this. So after this, we are going to introduce the next thing, which is called moments. Before this, if you have any questions, please ask me. Any questions you have? This is called moments and variables. No questions so far. These are very interesting things.
Sir, I have a doubt in the z equal to zi you defined above, like in the proving.
This are you saying? This one? This one are you saying? Z is equal to?
Yes, sir. Why is it taken that it is only positive and negative probabilities are 0?
Okay, fine. It's a good question. So suppose this is less than 0. Okay, you are taking some value of z such that zi prime is less than 0. Okay, then what will happen that P of z greater equal to 0, okay, union z is equal to zi. So this is a disjoint stuff. These two are disjoint events, right? Greater equal to 0 and this is negative. So these two are disjoint events. So, right? So this is equal to Pz greater equal to 0 plus Pz is equal to Zi prime. Right? Because these two are disjoint events. Now this is equal to 1. And their union is an event, so it has to be less equal to 1. So P of Z is equal to Zi prime is equal to 0. Their union, their summation, this summation plus this has to be less equal to 1. Right? Anything has event less equal to 1. And this is already is equal to 1. So this part has to be equal to 0. Is that okay?
So I have it that probability of Z greater than or equal to 0 is equal to 1.
Sorry, I didn't get you. Can you please repeat?
Why is the first one equal to 1?
So that is given. So it is given, you see, this is given. Px plus greater equal to y is equal to 1. It is given. That means Pz greater equal to 0 is 1. This is in our hypothesis, in our assumptions. You see that this is thing. P get x greater equal to y is equal to 1. That implies Pz greater equal to 0 is equal to 1. Is it fine?
Yes, sir.
Yeah, if you have any question, please ask me. Okay, you need to clarify all these things. Otherwise, the following stuff will be more difficult to you. And these are really interesting stuff. Okay, now moments and variance. So moment is actually some generalization of expectation. So generalizing expectation, we define moment. We define moment. So we have done all these things in details for expectation. So in moments we'll be little quickly, we'll do little quickly. So definition 1, X is said to be have a moment of order R if x power r is nothing but you are multiplying x r times, has finite expectation, and its rth moment of x. In this case, if it has finite expectation, is defined rth moment of x is defined as the expectation of x power r or e x power r. Okay, one remark which is really essential here. So if x has a moment of order r, and k less equal to r, then x has a moment of order k. So anything less equal to r has a moment, has finite expectation. So proof will be so suppose if mod x less equal to 1, then mod x power k is less equal to 1. If mod x greater equal to 1, as k is less equal to r, what is it? So mod x power, sorry, this is not mod xk. We put this k inside. It's equal to 1. That is obvious. In this case, this k which is equal to mod x power k, which is less equal to mod x power r, because k is less equal to r, and this is equal to mod of x power r. So mod of x power k is less equal to 1 plus mod of x power is x power r. So summation x mod x power k f of x is equal to summation x 1 plus mod x power r f of x is equal to e x power r. This we can do because x power r fx, this is finite, because x power r has finite expectation. So this is finite. So you can see that here x has a moment of order k because x power k has finite expectation. So, but it may happen that if something has moment of order r, doesn't imply it has a moment of order r plus 1. So if something is less equal to k is less equal to r, implies k has also x has also has a moment of order k. But if k is greater than r, then we cannot say anything. Then k may not have, then x may not have a moment of order k if k is greater than r. So we see one example for that. So this is a particular example. The sample space is natural numbers. X is a map from n to n, which is the identity n goes to n or x goes to x, and that probability density function or the probability mass function, which is by definition p x is equal to x. This is given as 1 by x power r plus 2 by n, where n is equal to summation 1 by x power r plus 2. Now this summation converges because these are all the natural numbers, and this summation converges because r is a natural number. R is greater equal to 1. Okay. Or even greater equal to 0 is also true. Okay, greater equal to 1. We need to greater equal to 1. So you can see easily that fx is a density function. We can prove easily because first of all this is non-negative function. In its summation, if you take just summation fx, that will be is nothing but summation 1 by x power r plus 2 by n, which is 1. So that's why this is a density function or probability mass function. Here, what is e x power r? That is summation x power r into 1 by into fx so equal to 1 to infinity, which is equal to r plus 2 by n, and which is summation 1 by x squared x is equal to 1 to infinity by n. But this upper infinite sum is converges, so this is finite. But if you take ex power r plus 1, you will get summation. Similarly, you will get not r, x is equal to 1 to infinity 1 by x by n, which is not, does not converge or infinity. So this is one example where the random variable x has a moment of order r, but not r plus 1. Okay, today I shall take 5 minutes more, telling at the beginning of the 5 minutes. So definition 2. Suppose x has a moment of order r, then what is the moment of order r means summation mod x power r f of x finite, this summation. So if you suppose ex, suppose mu, we know that mu is equal to, by definition of okay, we don't need even mu. So mu is any fixed number, is a constant, any fixed number. Okay, don't take the fixed number. This is actually mu is, there will be some confusion of notations. So mu is actually the expectation of x. It's a moment of order r, so means when r is equal to 1, it has also moment. So expectation is finite. In this case, summation mod x minus r, x minus mu power r, if x, which is equal to, you can prove I is equal to 0 to r. Then we break this summation. We can break this just using the binomial coefficients. R mod x power I mod mu power r minus I f of x, which is equal to I is equal to 0 to r. We take out this r, choose I, and mod mu, choose r minus I, summation x mod x power I f x. Each of this term, because I is varying from 0 to r, each of this term will be less than finite. So the total thing is also less than finite. So, so this is called the arith, or this is actually equal to expectation of the random variable x minus mu power r. So this is called the arith central random moment of central moment of x. So here mu is the expectation, or mean, we also say mean, or average. In many cases, you can think this as an average. Expectation you can think as an average. At least for uniform density, for discrete uniform density function, this is the average. It's central moment of x.
Sir?
Yes, sir.
Yes, sir, the time is...
Yeah, I understood. I understand the time is over, so I am stopping here. So we will take one extra class on Saturday at 3 p.m. Okay, we discussed in the last class, yesterday's class. So one extra class I will take this Saturday, 3 p.m. I will mail about this class to all of you. Any questions?
Sir,
Yeah,
no,
if you
sir,
have any
it
question,
will,
you can stay, others can leave. Yes, sir.
sir, it will not possible on the Saturday 3 p.m. because
Why?
we have additional class.
Which additional class you have?
Algorithm.
But I told yesterday no one said anything.
No, sir, it's fixed from first week onwards. So
Okay, so 3 to 4.
sorry, it's actually up to 5:30.
From which? From what 3?
Actually 4 to 5:30.
So it's okay. I'm taking the
एक
class
second,
from 3
एक
to
second.
4. Yeah. So yes, sir. Yes, also
Yes. So you are taking 3 to 4, right?
3 to 4 I'm taking. So I think there will be no problem.
Okay. Oh, that's 4 to 5:30.
Okay, then it's fine. Any more questions you have?
सर कॉलेज कब खुलेगा?
I hope that by July or August 2000 this year you all will return. I hope that because our director has told that to the first year students who are in first year now, that by August, means by before the autumn semester of this current first year, next autumn semester, they all will return. So I hope before them you will return. This much I know. And people are coming back.
Okay, sir.
Not BTech students, but the research scholars and postdocs, they are coming back now. Okay, anything else?
Yes, sir.
Anything else do you have to ask? Okay, so then we stop for today. We'll meet again this Saturday from 3 o'clock.